Okay. Now I did make a couple more comments. If you have a higher, you notice, among other things, that Q of t doesn't factor into this. Q of t doesn't have anything to do with this. Okay? It's only the P of t function. If you had a higher order equation, like a 7th order equation, then only the coefficient of the 6th order term would be here, but it would be very similar in that sense. And of course, a higher order equation can easily be transformed to a system, which is one way to kind of get from that statement to this statement, which is this: if you got a system, you know, this is an n-dimensional, y is an n-dimensional vector, P of t is an n by n matrix now, where the entries are coefficients of, or functions of t. They might be constant, so they'd be constant functions, but they don't have to be. Okay? Now the statement is very similar. The Wronskian, which is just the determinant of the Y matrix, you know, of a matrix consisting of column vectors that are form a fundamental set. Okay, put your fundamental set into a matrix, take the determinant. That's your Wronskian. Okay. So if you know the Wronskian at one point, you can find the Wronskian at any other point by doing this. Now, this is very much analogous to that integral of little p of t, right? Limits are the same, but in this case, we integrate the trace of the matrix. And you had a question about the trace. So I don't know who taught you linear algebra, but whoever did it didn't do enough with trace, apparently. I don't know, we got to find that guy. Okay. Trace of P of S. And your book has a bracket around P of S when they state this thing, which is in fine print. I had to look twice to see it. P of S is a matrix. It has a trace. You don't put a bracket around something that's already a matrix. Maybe I'm being ignorant, and it's very possible. But okay, trace of P of S. Is the sum of the diagonal elements, which is an invariant under similarity transformations. Go look at the video, digest that comment, and see what it means. I'm not going to worry about it today. Okay? Similarity transformations are important. We didn't get to diagonalization. In the context of systems. There's a lot we didn't do with systems. We did some Laplace transforms. So, you know, there's a little bit of a trade-off. And I'm still trying to feel my way through what we do in a 3-credit differential equations course. It's been dumbed down before. Okay?
Well, we still usually go about 10 minutes.
We have to do
anyway.
propagator matrices. Yeah, it's yeah. It's unsatisfying, but I think you're getting what you need. Okay? So there is Abel's theorem. Okay? Once we stated it for, it's over here probably off what you can see, but on the video, once we stated it for a 2nd order system, all the other statements come out in a fairly straightforward manner. But the reason you use a trace is probably a little bit mysterious. It probably will remain mysterious. Okay?